um, related to your giant metallic structure. Let's actually have a look at this giant molecular structure. The moment we enter this molecule, so we are going to talk about covalent compounds. Okay, so covalent compounds that we are going to talk about is going to be something related to this term, which is going to be allotropes. To make it simple, what are allotropes? Allotropes are having the same element with different arrangement. Okay, having the same element with different arrangement. So how many, like for example, the one inside your textbook was actually more towards carbon. Carbon can be arranged in many ways. Okay, to be exact, how many ways? To be exact, 1, 2, 3, 4, 5. There are 5 ways carbon can exist. Okay, they can exist in the commonly known, I think, diamond. I think the second one you should know also during IGCSE, you would have learned about diamond and graphite. Okay, but now, okay, apart from diamond and graphite, you should also know that carbon can also exist in graphene form. We will learn about this, graphene. They can also exist in fullerene. They can also exist in nanotube. Just now, if you recall, I have written in simple molecular part that we will learn more about fullerene and nanotube. Okay, so I have actually put it over there. They are simple molecular, but they are allotropes. Okay, they are allotropes. So that's why I'm putting it over here. Apart from these allotropes, okay, graphite, diamond, and graphene, we are going to also learn about another giant molecular structure, which is going to be silicon 4 oxide. Silicon 4 oxide is SiO2, okay, generally found in sand. And this SiO2 is used to make glass. Okay, they are used to make glass. So here, okay, if I look at graphite, okay, if I look at graphite, let's start with graphite. Yeah, so the allotropes of carbon, they are going to be arranged in planar layers. Planar means a single plane. It means in form of like, imagine this being one paper stacked on top of another paper, stacked with on top of another paper. If I want to push this paper out, okay, and then I want to actually push this paper out, you can push. Okay, why? Because the forces between them is going to be a bit weak. Okay, a bit weak. But if I want to tear this, okay, I can still tear, but it's going to be more difficult to tear. Okay, each paper, if I want to tear. So that is going to be, we are talking about trying to break the bonds over here. Okay, so there are two types of bonds over here. Okay, one bond is going to be VDW, van der Waals forces of attraction, between the layer and layer. Okay, between the layers and layers, there are van der Waals forces of attraction. Here, each of them, this is carbon, carbon, carbon. Okay, each of them, they have covalent bonding. Okay, covalent bonding. And you can see that they are arranged in hexagonal shape. Okay, that's why they say they are arranged in layers, arranged in hexagon. But let's actually look at this question. Each carbon is bonded to how many atoms of carbon? So if I look over here, how many atoms of carbon, Megan? One atom of carbon. How many atoms of carbon?
6.
No?
In
1, 2, 3. Can you see that?
oh,
Okay, there's only one atom of carbon is bonded to 3 atoms, other atoms of carbon. So it means, okay, we know carbon is going to be 6 electrons. Okay, so if I write 2, 4 valence electron. So imagine if you have 4 valence electron, what happens over here is one of the electron, they share over here, share over here, share over there. There is one more electron, okay, Audrey, you can go. Okay, one more electron will be on top, not being shared. Okay, so each of them, they will have one electron that is not being shared. So these are the electrons that will that will form the sea of delocalized electrons again. Okay, that's why if you look at the properties of graphite, they can conduct electricity. Why graphite can conduct electricity? Because there is cloud of delocalized electron. Okay, there is extra electrons over there. So in this case, each carbon, okay, is covalently bonded, okay, to 3 atoms of carbon. they do have high boiling point and melting point, but now, yeah, when we are talking about giant molecules, okay, please do not talk about van der Waals forces and so on. Anything giant ionic lattice, giant metallic, and so on, please do not talk about the van der Waals forces, dipole, and so on. When the moment they are giant, we need to talk about, okay, let's say if it is giant ionic lattice, why high melting point and boiling point? Because there is a lot of electrostatic forces of attraction needed to be broken throughout the lattice. So if I want to actually explain why the boiling point of graphite is really high, I need to explain there's a lot of covalent bonds that needed to be broken across the giant structure. Okay, so this one we are talking about covalent bonds. Okay, don't talk about, okay, the van der Waals forces, don't talk about other kind of forces. Okay, now, so that is going to be high boiling point and melting point, easily scratch or slippery. Why? Because weak van der Waals forces. So these van der Waals forces can be broken easily compared to the covalent forces of attraction. Okay, so this one you can slide on top of each other. Okay, and this is also going to give rise to, I think, graphite. If you compare with the diamond, the boiling point and melting point, graphite, even though having high boiling point and melting point, they are still lower compared to diamond. Okay, why is lower? Because the arrangement, because they are arranged in layers. Okay, because of the VDW. Okay, so generally diamond and graphite, they have high boiling point and melting point. Okay, but okay, in comparison, diamond is harder. They are much more higher boiling point and melting point. Why? Okay, I think because of the structure being repeated again and again. Okay, so you see this structure. You can see each of them, they have a tetrahedral structure. If each one carbon bonded to how many carbon? 1, 2, 3, 4. Okay, so there are 4, and that makes that all the electrons, the 4 electrons, are completely being used, so they cannot conduct electricity. There's no sea of delocalized electron. So if I put it over here, each carbon atom is covalently bonded, okay, to other 4 carbon atoms. The carbon atoms are arranged in tetrahedral shape, and the regular arrangement gives them this crystalline structure. This crystalline structure and all this arrangement, they are making it harder, and because there is no delocalized electron, they cannot conduct electricity. So I hope you can understand this. Okay, so this part we have covered.